Okay, we're nearly finished with the parallel RC circuit. One of the last things that we have to do with this circuit, of course, is to analyse what happens about the impedance phasor. You know, we've got our circuit drawn up, and in the experiment that we've just conducted, we used a sampling resistor of 10 ohms, and we measured the voltage drop across that, divided it by the 10 ohms. That gave us the current flowing in the circuit. And I've got some notes here that I did make on paper, so I'm just going to refer to those and put some values on the screen. We can never get the marker. Alright, so we had 900 hertz coming in, and then we had an AC current happening in that part and an AC current happening in that part, and of course the AC current circulating throughout the circuit. And most importantly, here's our sampling resistor. That goes to the oscilloscope, and that gave us the value we're after. We had IC we'd previously measured at 2.77 milliamps, and we measured IR before at 4.9 milliamps. And the vectorial sum of those, that is the square root of the IR squared added to the square root of, or the square root of the whole lot, IC squared. So the IR squared plus IC squared, take the square root of that, and that will give us the vectorial addition, which came to 5.63 milliamps. We did it in theory, and then we did it with the oscilloscope in this lab, and it worked out exactly correct. If we plot this on a phasor diagram then, IR at 4.9 milliamps, and then IC at 2.77, so that's going to be about there. And then dot, 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 dot. And then the resultant coming up here, which represents I total, and that was that 5.6 milliamps there for I total. So far, everything works out fine. Going great, and then somebody asked that amazing question, sir, how do we draw the impedance phasor diagram? So one gets the pen and one goes, it's not that easy. We don't generally have an impedance phasor diagram for parallel circuits. Now, if we want to do that, we have to do what's called a parallel to series translation, first of all. Going to put a couple of things up on the board then to look at what we have to do for that. And the first one, REQ. And look, maybe I'll just make some space because we know that we've got 900 hertz flowing in there. We'll rub this part of our diagram off the board. Haven't got a very big board to work on here. REQ equals Z cos theta and XC, XC EQ equals the impedance times the sine of theta. We worked out the impedance already because Z, of course, just like R equals V on I, equals Vs divided by IT. And we had 4.9 volts of source voltage at 900 hertz. 4.9 volts divided by, again, this amazing 5.6 milliamps, and that gave me an impedance of 870 ohms. 870 ohms impedance. So using these equations down here, I have to get that impedance and I have to multiply it by the cosine of the phase angle. Now the phase angle there, probably I got this very easily when I used the rectangular to polar translation on my calculator by putting in the polar coordinates putting in the rectangular coordinates and then getting the polar coordinates, and at the same time the calculator gives me that phase angle. Now the phase angle I got for this, and we've done this plenty of times, was 29.48 degrees. And that's going to do this in here, 29.48 degrees. So I've got to take the cosine of that and multiply it by the 870 ohms. And that'll give me REQ. And REQ today worked out at being 757 ohms. What are we doing here though? What is this REQ and XCEQ? Why are we doing this? And let's just put a bit of a heading up here. I think that we really need to get rid of a bit more stuff on the board. I think we can get rid of that. We can get rid of that. And maybe at this time, we need to use a nice red texture colour. And so this is going to be equal to, how about that? Oh, there it is there. So we had 1K and we had 0.1 microfarad. Over here, we're going to get a series equivalent circuit. So REQ, 757 ohms. 757 ohms. XCEQ, I've got to get the impedance, which was 870 ohms. And I'm going to multiply that impedance by the sine of 29.48. The sine of 29.48 times that happened to equal 428 ohms. .428 ohms XCEQ. It'd be nice to do a bit more maths on that and find out exactly what the value of that component is in capacitance. Because if we have to build this circuit up, it's going to be easy to make up 757 ohms, but we can't just go to the shelf and pick up a 428 ohm XC capacitor unless we do some maths on that first. So we do some maths on that quickly. We just transpose the XC equation. And of course, XC equation equals 1 on 2 pi FC. And after we transpose that and we play and do the maths on it, I came up with 0.412 microfarad. .412 microfarad for this. Remember, originally we had 0.1 microfarad, 1K, equivalent circuit, 757 ohms, 428 ohms XC, which gives us 0.412. microfarads over there. And then, where we started was, that question had been asked, so how do you do the impedance phasor diagram for this wretched parallel RC circuit? Well, how about we try and do that? We had our parallel current phasor diagram happening here. Going to rub some things out over here. I wish I had a bigger board, but, well, I don't. So I'm stuck with what I've got. Let's do some new axes. And this time, I'm going to be down in this quadrant because I'm playing with a series RC circuit. and this is going to be XC, and this is going to be R, and somewhere here I'm going to have Z with a phase angle. Oh, things are all mixed up now, aren't they? Our previous diagram had the current, we had the capacitor current leading the circuit current, and the total current supplied, of course, the phase angle of the circuit, the difference between the total circuit current and the supply current. But now we've got things happening in the other quadrant down here. So R, 757 ohms, 757, R at XC at 428, it's going to be about there, dash, 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 428, resultant over to there. There's theta. If we plug this into the calculator and we go rectangular to polar, so always be R first, 757, 428, we'll come up with the impedance, which works out to be, happily enough, 870 ohms, which I'd rubbed it off the board. We had that 870 before that we worked out with Ohm's law. This also works back to 870 ohms, absolutely amazing, and the phase angle works out to be 29.48 degrees. So you probably wouldn't be drawing a phasor diagram for it, but if you did, that would represent the phasor diagram for the equivalent series circuit from this original parallel circuit, parallel to series transformation, and then constructing the impedance diagram. Now we've got the current phasor, we've got the impedance phasor, we've done the maths, was based on REQ equals the impedance of the circuit times the cosine of the phase angle, and XCEQ, the impedance of the circuit times the sine of the phase angle. This has been Greg Moore for New South Wales TAFE. I hope that wasn't too hard to digest, and I hope you enjoyed it. Thank you very much.